Okay, should I begin now?
Yes.
Excellent. Okay. So my name is Rob Newport, recent graduate of the lab. And today I'd like to talk about quantum neurobiology. And I want to start off with a saying by Richard Feynman, which is, I can safely say that nobody understands quantum mechanics. And this goes really, really big time for me. So I don't want to come off as pretending that I'm an expert. This is a field that I am just now kind of getting into for some reasons that I'm going to talk about in the presentation. However, I think it'll be really interesting for you guys too. And I'm just going to talk about one sliver of one little thing that I read through, and hopefully it might spark some interest in you too. So the reason why I became interested in this topic is for two reasons. One is I'm in a fencing club, and I just met this guy. We ended up being friends, and it just so happened that he is through sheer coincidence, he is a CSIRO scientist, and he's looking at partnerships in quantum applications in neuroscience. Just totally coincidental that he's also looking at manufacturing, and this is something that I'm also kind of dabbling in as well. So just through sheer luck, we are in this very, very fringe kind of interest together, and we discussed some topics, and so these led to some readings. Yes.
Yes, sorry to interrupt. Just in case you haven't noticed, actually, like Eugene is also like a present here.
He is. Okay, all right.
So
sorry. I can't see. In the video, I can only see like tiny little blips of people. So yeah, no, that's great. I'm really happy then. Okay.
Thanks.
Okay, cool. And also, I was invited to collaborate on a paper on the historical progression of the CIA's Stargate program with the University of Virginia's Department of Perceptual Studies. As you guys know, my thesis was in human perception and salience. So this was naturally a topic that was of interest to me. The CIA had some really weird and interesting experiments in the 70s, 80s, and 90s, and that kind of led me to think like, how did these experiments work? So that led me to read some papers also within the field of quantum neurobiology. So these two connections led me to reading these, what I think are two important papers, and that is written here. And I'll give you guys this presentation so you can explore it in more detail if you want to. First of all, I'm going to go into what conventional wisdom dictates. And so, our understanding is that cognition emerges from complex synaptic interactions between neurons, right? And that relevant neuronal information is completely membrane-based. In other words, it's purely within the surface of that neuron. And the synaptic strengths that mediate memory and learning are basically around those connections within those neurons. And that when you look at them as a whole, there's a kind of probability connected to other probabilities, that kind of reflect this classical Bayesian probability matrix, okay, which we call a Bayesian network. And these are all the traditional understandings. However, if we go a little bit deeper, especially when it comes to perception, which is a field that I studied personally, what we're really doing is orchestrating these sensory inputs, and we're combining them to create a cognitive process. And a collection of these processes we can loosely term consciousness, right? Now, another couple terms I just want to get you guys familiar with are biophotons, which are the photons of light in the ultraviolet and low visible light range that are produced by a biological system. This, I mean, depending on what you've read, this may be surprising or interesting. And also that there's a general definition of a phonon, which is a definitive discrete unit of quantum vibrational mechanical energy. And so these two unusual words are going to be coming up again later in this presentation. So at first, it was believed that biological systems are too warm and wet to support quantum biology. Now, I should kind of separate quantum mechanics to describe mental processes versus actual quantum biology. Now, it may be that, when you first saw this, you thought, oh, okay, we're going to look at the quantum mathematics to describe what's going on in the cognitive process, which, a lot of people have been talking about, for quite a while. But what I'd like to focus on is something a bit deeper than that, which is the quantum biology of what might be going on an intracellular process. So this is a bit more, this is different to that. This is not just the emulation of consciousness, which you could do with quantum mathematics. It's the simulation or the actual representation of quantum mathematics within biological systems. This is quite different. This is, quite a bit more significant. So according to Solardo and others, later studies prove that thermal energy may assist rather than disrupt that particular quantum process within the actual biology. One of the first kind of problems within conventional wisdom when it comes to, thoughts and cognition arising from this connection of neuronal synapses is that paramecium, which are single-celled organisms, I'm sure we all know, have displayed very kind of cognitive behaviors, especially when it comes to, hunting, the mating process, bumping into things. I'm sure we've all seen paramecium and we've thought, oh, what a cute little animal. Like they're so kind of behavioral, right? But they have no synapses. So then, where does this cognition stem from, right? I mean, this is a really interesting topic that Hameroff discussed within his presentation at the Center for Theoretical Neuroscience at Berkeley in 2013. So he proposed that cognition was happening through a ciliary membrane. Now, I'm not going to go too deep into this because, of course, it's a massive topic, but what I'd like to focus on are the dynamics within the motor proteins within this ciliary membrane, because I have a very interesting proposition when it comes to this. But basically, what I want you to kind of just in your short-term memory understand is that within each one of these hairs in this paramecium exists a bundle of microtubules which have these interesting motor proteins that go up and down. So these optical and vibrational synapses are generated by biophotons, and their elastic vibrations are within the tubulins. And the dynamic within those microtubules are motivated by the phonons that go on within the cilia. And so this is kind of the crux of what I'm trying to get at here, is that these microtubules work as a highway for the kinesin and dianin within the cilia to basically create movement up and down within these microtubules. And the interesting thing is that the kind of energy transfer that goes on in this process appears to be both guided by the tau proteins, which I'm going to talk about a little bit later, and could also be kind of a interesting allegory for cognition. So just in case you guys aren't familiar with what tau is, so the tubulin associated unit is one of the primary kind of drivers behind what we think of. So problems with those are one of the primary drivers between what we think are behind things like dementia, autism, and other kinds of cognitive pathology. And the interesting thing is that we thought for a long time that this was due to amyloid plaques, or that there was some kind of inflammatory response that was retarding or perhaps jumbling up these filaments within the brain. But what appears to be kind of showing itself is that it has to do with what is inside these neurons, which are these microtubules, and that perturbations or problems or disruptions or damage to these microtubules have a massive impact on cognition. So the evidence of this exists within tryptophan residues that are seen within the cytophyte membrane in algae, and this is seen in choline and others. They have shown that the distribution of tryptophan residues seem to support quantum coherent transfer and electronic excitation. This seems to imply that there is a actual biological quantum dynamic happening intracellularly. And also, a closely packed group of molecules can collectively donate this excitation, leading to a super transfer excitation of energy. So this is also kind of very tantalizing to kind of understand the dynamics behind brain cognition. And I think we need to, I think it also kind of points to looking past the neuronal membrane as the endpoint for where things like memories or cognition happen. And perhaps we should look a little deeper into the intraneuronal microtubules within the cognition process. The other kind of takeaway is that mental activity more closely resembles quantum rather than Bayesian models. So, you know, it seems like there's still a lot of discussion within contemporary papers that cognition, especially when it comes to perception and visual pattern recognition, a lot of them still follow, you know, the scan match Bayesian model rather than looking at a more quantum model. And when we're looking at theoretical neuroscience, it seems like consciousness and cognition are likely to involve scale invariant fractal-like representations. I put this in quotes because I didn't want you guys thinking, you know, because I write a lot about fractals, I didn't want you guys thinking that I'm kind of shoehorning fractals into this. No, this is an exact quote taken by Hameroff during his discussion at UC Berkeley in 2013, that representations from intraneuronal microtubules to large-scale network configurations will involve scale-invariant fractal-like representations, probably due to their self-similarity and the compression of that self-similarity and how it would, you know, benefit the network. So the other thing that I think, if I don't know if there are any clinicians in the group, but it may seem like microtubule integrity can increase the effectiveness of new neurological and psychological therapies. So I don't know if there are any I can't see if there are any clinicians in the group, but I don't know if that's already being done or if that's being considered. But you know, this is kind of outside of the domain of my expertise, because I'm not sure what is currently in practice right now. So for future state, this is, I think, the most interesting for me is, you know, on the clinical side, can we repair or augment cellular signaling by looking deeper into these microtubules, especially when it comes to augmenting expertise or perhaps even treating dementia? In industrial applications, I think that there's a really interesting potential to create a proof of concept, especially using the dianin and kinesin to replicate TCP/IP packet delivery. Just like with packets, there's incoming and outgoing packets, and the dianin and kinesin motor proteins look like they only go one direction as well. So there may be some really interesting potential there to create a wet network. And the other interesting kind of scientific future state could be that are cilia and centrioles quantum optical devices? So in these single cell organisms, you've got those tiny little hairs kind of moving around. Are those is there some kind of phonon biophoton transfer going on? Are they little eyes? And can we create cameras like that? You know, that I think that would be very, very interesting, both from a scientific and also industrial application. So definitely a lot of things to think about there. And I again don't want to come off like I'm an expert or that I know all about this, because you know, I'm definitely just dipping my toe into this subject, but I do have that background in perception, so I find this very interesting from a perception and cognition kind of background. So with that, do you guys have any questions? I'm sure, you know, you've got some questions I don't know the answer to, but I'd love to hear them anyway.
Can I book a meeting with you?
It's like great presentation, just like blocked my mind. I've such a difficult time to follow.
Yeah, the interesting thing is that the whole human